Okay, hello again. We're going to do part 2 of this counting cells thing, and we're going to move on to the cytoplasm. We're going to look at this cell body as well as the nuclei. So let's bring up our maximum projection, and we're going to pull out just the red channel in this case here, and we don't want that, and we'll call this cyto. Okay, right, so we're going to analyze the cell bodies now, and this is normally where I would lead off into Cell Profiler, and we'll come back to that, and we'll do a whole another line of Cell Profiler tutorials. Cell Profiler does a good job of starting from a seed point like a nuclei and working its way outwards. Whereas, as far as I know, it's not particularly easy in Fiji, and you'll see that it's not as sharp a distinguished boundary, or is not as well traced boundary when using Fiji, and we'll just do it, and it works well for the basic stuff when it's not too complicated. And then next time around we'll find something which is complicated, and Fiji will do wonders on it, hopefully. So we've got our cytoplasm channel here, and we'll do a threshold and move from there. You can do the smoothing on the edge. It depends if you need it. Sometimes it will make life easier, sometimes it doesn't. Depends on what you have and what kind of signal noise you have. Again, we'll change it to greys so it's not misleading on our eyes and on the threshold. So here's our threshold, and we want to pick a region of the threshold that doesn't start to break up across the boundary and round the outside of the cells. So we'll go somewhere here, and you can start to see when there's more data here on this histogram that you have this background, and then this data kind of sections of the histogram, and you'll see it somewhere up here. It looks good. Again, you can use one of the statistical separation or threshold identification types here. Let me just see what some of them look like, and I think maybe the Otsu is a good one, or Lee maybe. Yeah. So we'll go with that for now, and then this time we're going to hit apply, and it's going to turn it into a what's called a binary mask, and technically there should be zeros and ones. If you look here, it's 0 in the background when I look at my value up the top here on the ImageJ window, and the value itself is 255 for the black. This is the inverse, and you can see at the top it's inverting the LUT for this mask, and this is the inverse of a standard grayscale lookup table where 255 in this 8-bit range would be white and 0 would be black. So it's the other way around. It doesn't matter too much. So what we're going to do is try and fill in these gaps. So now it's a binary image. All of these binary options in here make sense. And it does some cool things, and a road makes it smaller, dilate makes it bigger, and open and close do a combination of these two in a clever way. So I think the best way to do it before you do the fill holes, which does as it says, fills the holes in these subjects, but if you do the close option, it gets rid of a lot of the small stuff, and it makes the fill holes work better. So you can do the close and then fill holes, and you're left with just the background of the cells, but it's got a boundary set with a threshold in a slightly better place. You probably could have gotten a similar completely filled threshold for the cell area here, but the outside might be weird, and it starts to lose some of the detail around and pick up on the background. So this combination can be useful. So now what we're going to do is we're going to go to this binary method again, and we're going to watershed. So it's going to go across and try and create channels as if you're filling up the data set with water, and where it would cross over. So it's going to create a channel where it starts to find a crossover between the two. And that's what you would use to separate the regions. It's done really well for this channel section of 3 here down the middle. Excuse me. And it's not done so well on the outside here. Let's get our image back here. So for the ones up here, it's not done a great job of splitting things out. There's a lot of kind of overlap, and clearly there's one cell here, and it's got these cells across here that look like some northern states with straight lines, and so it's not done a great job. When we go to cell profile, you'll see it does a much better job. It's obviously very difficult for a computer to distinguish these. We can pick up the patterns, but based on intensity and without intelligent kind of inferences from the shape in these algorithms, you can't really do much with it. So this is what you get here from separating out just the basic 3 cells down the middle here. And you can go ahead and do the analyze particles on this one. So bring in the image you want to the front there, analyze particles, and now what we would want to do is try and not include these smaller ones. Can we use a combination? We can use a combination of size and circularity, and so these will need to be played with. And I'm going to guess on this to be, let's just try maybe I don't know, 3,000, just a guess, and then we'll keep the ones that are more round, and so we'll get some of these straighter ones, so we'll have 0.2 maybe a guess here. Okay. We don't want to save those measurements forward right now, and so it's included everything, so I don't have my size right. You can kind of measure the pixels across somehow. There are different ways you can do that with using the selection tools and align profiles. I normally find it's quicker just trial and error. Let's see how we do. So we're starting to lose some of the smaller ones there. One more time, let's just go for it. No, still not gone high enough. Let's keep going. Right, now we're starting to get to the regime where we're including what we want here, but we're missing out something we want here. So we're not able to distinguish between these two, which are similar size. So this is where it starts to sort of break down, and I don't seem to go too well with Fiji, but it does work for some easily separatable cells. If they're very sparse, you're going to get great results with this straight off, and you can get the measurements here from the areas. And it's always good to do a control on the areas to know whether these are in micrometer squared or pixel squared. There's another YouTube we've done on scale bars that includes information about the scaling factors. But if you go up to the properties, I always get these two mixed up, properties and information, you can see it's got the pixel widths in here in micrometers, so it knows what they are. If I were to do the control, if I change these back to 1, and we don't care too much about the voxels and the depth, we're not looking at the Z in this case, and 1. So now this image is 512 microns by 512 microns, so I've screwed with the scale, and if I do my process and then measure, oh sorry, I need to do analyze particles, didn't I? And it's not clear the results. And we'll do it again, and we see that the new results, these two lines, show the same as these two, 1 and 2, 4 and 5, this one was everything, show that the values in pixels. So that's a way of verifying that these values are in micrometers and not pixels, and just to make sure, you need to do that probably once per set of data that you have, folder of data, just to verify you've got the right numbers. Okay.